Hi everyone, welcome back to my YouTube channel. I am Preeti and I'm back with another lecture in the DBMS series. So without any further ado, let's get started. Now, what is this query optimization and why do we even need it? So whenever we want to improve the efficiency of our query, make it execute faster and consume fewer resources, we use the query optimization techniques. So whenever we want to increase the efficiency of our query, make our query to execute faster and give results in faster time. And whenever we want to consume some fewer resources of our system, we use this query optimization technique. So consider if there is an employee table, and in that particular table we have some employee details such as employee ID, employee name, employee age, and much more fields. Now consider that this employee table has 1000 records. And in that 1000 record, I make a query that give me the details of employee whose employee ID is 990. So I want to fetch the detail of employee whose employee ID is 990. So it will go ahead and it will do a search on the employee ID and it will see row by row that wherever EID matches 990, it will return the entire result of this particular row. But this query may take some time. And consider that in real scenario, our employee table has 1 lakh or 10 lakh plus records, right? So for that, we need to make our queries to execute faster so that we can get the faster result. That is why we use the query optimization techniques. So optimizing SQL queries is essential for improving the performance of database application. So whenever we want to improve the performance of our database application, we need to optimize our SQL queries and we can use the query optimization techniques there. So let's see what are the common techniques which we use. So first one is use indexes efficiently. So index the column frequently used in where, join, order by, group by clauses to speed up the data retrieval. Now what is this indexing? Indexing is basically a technique in which we lower down the number of disk access which was being used earlier. So it lowered down the number of disk access, because of which the queries gives us the result in faster duration of time. For now, if you're not understanding indexing, don't worry, we'll be having a dedicated lecture on indexing and types of indexing. There the concepts would be clear. But for now, you can only understand that whenever we are doing any group by, where, order by clauses, it's better to use the indexed columns there to get the faster result. Now coming to the second point, that is select only necessary columns. So avoid using select star, especially only the columns you need in your query. This reduces the amount of data transferred and processed. So most of the cases we use the select star to fetch some of the details. But if we know that we have to fetch only some specific columns, it's better to provide the columns rather than providing a select star, which will go ahead and fetch all the details or all the attributes which is present for that particular employee or for that particular XYZ entity. So we should take care that if we want only specific columns, it's better to use that particular columns with the select statement rather than using the select star. Now coming to the third point, that is optimize join operations. So choose the right join type and use indexed columns in the join condition. Now what is join? So basically in join what we do is consider if there are two tables A and B and I want some details from A as well as B table, I'll perform a join operation between them on the basis of a common entities, or you can say common attribute which is common between both the tables. Now it says that whenever you are performing the join operation, always take care that you choose the right join type. And second thing, if you are joining on basis of some column, always make sure that that particular column is an indexed column so that the number of disk access lower down and we can get the queries result faster. So we perform join whenever we want some related rows of different tables, and on the basis of parameter or on the basis of a related column on which we are joining, that should be indexed. Now coming to the fourth point, that is partitioning large tables. So for very large tables, consider partitioning them to improve the query performance. Partitioning allows the database management system to scan only relevant partition, reducing input-output cost and improving the response time. So it says that if your database is too big, so partition that into smaller chunks and then make a query on that smaller chunks so that you can get the result faster. It will reduce the input-output cost as well as the response time. Now coming to the fifth point, that is cache the results. So cache the results of frequently executed queries to avoid the redundant calculations. Says if there is any query which is getting executed as part of different API calls, so it's better to call a cache rather than calling a DB, because calling to the DB may take more time, but if the response is stored in the cache, for consider X duration of time for the similar query, it's better to call the cache so that we can get the result faster and also we can avoid some redundant calculations. So let's learn about physical storage and file organization. So what is a storage device? For storing the data, there are different types of storage operations which is available. So storage device basically help us to store the data. Now what are all the options which are available? So first one is primary storage, second is secondary, and third one is tertiary. Now coming to primary storage. So it is basically the main memory and the cache memory. It is fastest, it is expensive, and as soon as the system leads to a power cut or crash, the data also gets lost. So data is only stored in the system until or unless there is a system crash or power failure. After that, the data is lost. Now coming to secondary storage, it consists of flash memory and magnetic disk storage, which is non-volatile. Non-volatile basically means that it saves the result even after there is a system crash or you can say power failure. So it stores the data permanently, and this is volatile because it loses the data once there is a power failure or system crash. Now coming to the tertiary storage, so it basically involves optical disk and magnetic tape. It is used for data backup and storing large data offline. So whenever you want to store large data, you use this tertiary storage. Whenever you want to store the data permanently, you use this volatile or you can say secondary storage. And whenever you want to store data for some duration, you can use this primary storage. Although primary storage is the fastest, but it is also expensive. Now databases store data in files on disk. So there are some disk which is present. You can say hard disk. In that disk, there are some files in which the data is stored. So each table or index may correspond to one or more files. Each file has a sequence of record. So each file consists of some sequence of record. Now accessing data from RAM is much faster than accessing data from a hard disk or SSD. So what happens is there is a CPU which access some data from the hard disk or from the SSD. But CPU is very fast and this hard disk or SSD is very slow. So it's better that CPU don't make a direct query to the hard disk. It go to the RAM and RAM makes a query to the hard disk so that this particular process is streamlined. So here you can see this is because RAM is designed for high speed read and write operation. Data retrieval in RAM typically involve fetching data in nanoseconds. So in RAM you can fetch the data in nanoseconds. So CPU makes the queries to the RAM and RAM checks if it has the desired result. If it doesn't has, it goes to the hard disk, it takes the blocks and it does the query checks if it has the desired results or not. Now RAM provides fast volatile memory for quick data retrieval. So volatile here means that after a system crash or failure, the data will be lost. Now data is accessed via addressable location and cache memory enhances speed. So the cache memory enhances the speed and data retrieval is done based on the addressable location. Now what is hard disk? So it provides a slower non-volatile storage with mechanical components that impact the access speed. So since CPU can't do a access on the hard disk itself or can't do a query on the hard disk itself, it goes via RAM because RAM is very fast and hard disk is comparatively slow. So data retrieval involves moving the read-write head and waiting for the disk rotation. So data retrieval basically involves moving the read-write head and waiting for the disk rotation. Now, when a program or application needs to access data, it first checks if the data is available in the RAM. If the data is not available in the RAM, it must be loaded from a slower storage device like hard disk or SSD. Index file in database management system are stored on the disk but are also managed in RAM to optimize the performance. Let's see that when we give query, how we get our results back. So here the query is fetch the detail of the student whose roll number is equal to 5. So there is a student table which is present and I want to fetch the detail of a student whose roll number is 5. So how the query will be executing? So firstly, the student table would be present in the hard disk because hard disk is a non-volatile memory. So it will save the data even if there is a system crash or failure. So it will save the data permanently. So we'll store this particular table in the hard disk. Now inside the table there are multiple records. So we store this particular records in some blocks. So there are blocks like B1, B2, B3 till Bn. So there are a couple of blocks in our hard disk and in each block we store some data. Consider in this block we are storing from 1 to 5 roll number, then from 5 to 10, then from 10 to 15. In all these blocks we store all these particular records. Now what will happen once the CPU receives the query? It will make a call to the RAM. it will say that I want the detail of a student whose roll number is 5. Now RAM will call the hard disk, and hard disk will give all the blocks one by one, like first B1 is given, then B2, then B3, and in this blocks it will search that if there is any student with roll number 5 existing. Once it finds the student with roll number 5 existing, it will take up all the details and it will give it back to the CPU, and then we can get the desired result. So this is how it functions. We use the RAM because the access is very fast, and this is a volatile memory, so it won't be staying so long, like after the system failure or a switch. This is how the query execution happens. Whenever we give a query, it goes to the CPU. Now CPU makes the call to the RAM makes the call to the hard disk. Each and every block is transferred one by one, and it checks in the block that if the query satisfies. When it checks that if the query has satisfied, it gives away the processed result. So how files is organized? So here you can see that there is a hard disk and there is a DB, or you can say table. Now in this hard disk there would be multiple blocks B1, B2, B3 till Bn. Now in this particular block B1, how much data of this particular table could be stored? How we can find that? So files are basically allocated on the hard disk in a contiguous blocks to reduce the fragmentation. Now number of records stored in each block is equal to size of block divided by the size of. So consider if there are 10 records here and size of each block is 100. So what we will do is we'll do 100 divided by 10, that is size of block divided by size of record. So it is 10. So in each block we can store at least 10 records. So this is how we find that in each block how many records we can store. So records can be stored in two ways. First is sorted way, searching is fast. Second is unsorted way, where searching is slow and insertion is fast. So we can store the data in a sorted or unsorted manner. In sorted manner the searching will be fast. In unsorted manner the searching will be slow, but the insertion would be fast. So this is how we can optimize our query and organize the files in our system. Now the very first question which would be coming to your mind is, why do we even need a indexing? So let's take an example of a textbook. So imagine you have a 1000-page textbook and you want to search for a specific topic XYZ. So you are having a book. In that particular book I ask you to search about a given topic XYZ. Now how you can do that? So first thing is, whenever we have the index or the contents of the book, we can go ahead and see that where that particular topic is present, and we can go to the page number. Consider a case where you don't have the index which is present in the book. Now in that case what you will do is you will search each and every page one by one. Now there are 1000 pages in the book, so consider the time you would be consuming when you are searching for each and every page one by one. So here indexing comes into picture. So when the indexing is not present, you need to manually search for each term in the book, which could be frustrating and time consuming. Now the second case is when the indexing is present. The index allows you to quickly locate each topic. You can look up for XYZ, find that which is page number where it is covered. This makes it more efficient and less time consuming. So you'll get a range of page numbers. In that particular page number range, you can just go ahead and search for that particular topic. Now here you can see that here you are hardly searching for 2 or 3 pages, but earlier you need to search for 1000 pages. So you can see the search space has also reduced and the time consumed is also reduced. So this is how indexing helps us. So indexing is a critical technique in database management system that significantly improves the performance of query operations by minimizing the number of disk access. Index table is always sorted. Now what does this mean, minimizing the number of disk access? So every data of us is present in our hard disk, or you can say in our disk. Now in this particular disk we have our database. Now in this particular database there are some tables. In that particular table there are some rows, there are some columns, and they are stored in the form of blocks B1, B2, B3, which I discussed in the last video. Now you need to go to each and every block to find a particular topic or a particular key. Now here you can see that when you have an indexing which is present, which says that if you want to search for XYZ, it's present in block B2. So you'll directly go to block B2 and just search for that particular topic or that particular key. Rather than going to each block one by one, you just need to go to one block. So you can see that it minimizes the number of disk access. So the number of disk we are accessing or the number of blocks we are accessing is very much minimized. Now why do we need indexing? So in the same way how we have used indexing in the book, it helps us to find specific records or data entries in a large table or large data set. So consider if you have a large data set in which consider you have 10,000 rows. Now in this 10,000 rows you don't need to go ahead and search for each and every row manually. Rather you can go to the index table and search for a specific key, and then pointing to that specific key you can go to the block pointer where that that particular row is stored in the hard disk. So you can go to that particular block. So here you can see that you provide a search key and the data access in the index table. Now in the search key, it is used to find the record, and data access, it contains the address where the data item is stored in the memory for the provided search key. So basically we have an index table in which we have a search key and the block pointers or the references to that particular data. Whenever we are searching for any key, it will come to this search key column. It will search for that particular key, then it will go to the block where that particular record is present, and then it will fetch that particular block in the memory. It will search for that particular value. Once it gets that, it will go ahead and send us in the final result. So the search key helps in finding what a user is looking for, and the data access tells us where the record is stored in the memory. It is basically a set of pointers holding the address of the blocks. So all these blocks have some address, and that is stored in the index table. Now how the indexing helps? So it helps in improving the query performance. Indexes allows the database management system to locate and retrieve data much more quickly than it could by scanning the entire table. So earlier what we were doing is we were scanning the entire table, or you can say entire blocks in which all the records are present. Now we only need to go to this index table. We need to search for that particular key which we are searching, and then we need to go to the pointing block where that particular value could be present, and then we only need to search for that particular block. So earlier we are searching for each and every block. Now we only need to search for one or two blocks specifically. Now indexes can be used to optimize queries that sort the data, that is order by, or group the data, that is group by. So as I told in the earlier slides, that index table is always sorted. So whenever we are putting any key which is present in this index table in the key column, they are always sorted. So this is a sorted data. So whenever we want our sorted data or a grouped data, we use index because that is very helpful. So whenever an index is available on the column being sorted or grouped, the DBMS can retrieve the data in the desired order directly from the index, eliminating the need for additional sorting operations. So earlier, whenever you want some sorted data based on some specific column, you need to perform some additional sort operations. But as the index table is always sorted, the key present in index table is always sorted, we can use this index table, or we can use the column on which this particular table is indexed, and that particular column, if we use with the order by and group by clause, it will help me to get my data more fastly and efficiently. Now we have certain indexing methods like dense indexing, where index entry is present for all the records, and sparse indexing, where the index entries are present only for a subset of records in the index. So let's learn about dense indexing and sparse indexing, like how we can store a particular key as well as their search pointers in our index table in different methods. So first one is sparse index. So sparse index is a type of database indexing technique where the index does not include an entry for every single record in the database. Instead, it contains entry only for some of the records, typically one entry per block. So consider that in our database we have some columns where ID is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now what we are doing is from ID 1 to ID 3 we are storing in block B1. From ID 4 to ID 6 we are storing in block B2. From ID 7 to ID 10 we are storing in block B3. So what we are doing is we are only providing the first element of that particular block in our index table. So here in the index table I have stored all the first elements of different blocks, and whenever I want to search for a value, consider 3, I'll go to this particular index column, I'll see there is a 1 present, and then I'll go to here, I'll see that there is 4 present. So basically between 1 to 4, 3 would be lying, so 3 would be lying in this particular block. So it happens whenever our data is sorted. So whenever we have a sorted data, we can use the sparse index where we don't need to store the value or store the entry for each and every record which is present in our blocks. Rather, we can store only the first element of the block, and we can give the block pointer where that particular entry is stored in our database or in our disk. So if we need to provide entry for each and every row which is present in our block, it will make the index table a much more bigger table, and then again we need to go through each and every entry, and then only we can search for that particular data. So it will also take more time than the sparse index. In dense index we does the same. We include the entry of each and every record which is present in our table in the indexing table. So in sparse index we only give or provide the entry for, you can say, some specific or single record which is present in each block pointer, so you can say a subset of records. But in dense index, we need to provide an entry for each and every record which is present in our database table or the table which is present in our hard disk. Now, which have an entry for every record. So dense index have an entry for every record. Sparse index have an entry for only single records of each particular blocks, or you can say it contains entry for only some of the records. Now, it is used when we have an ordered data set. So whenever we have an ordered or sorted data set, we only use this particular sparse index. If the data set is not ordered, how can I say that I'll give 1 and 4, and if I want to find 3, I can go to this particular block, right? Because the data is not sorted. So when the data is not sorted, we don't use sparse index, but when the data is sorted or ordered, we use the sparse index. So if a table has 1000 rows and it is divided into 100 blocks, you can create a sparse index. The index might have only 100 entries, with each entry pointing to the first record in the block. Now it says that consider our table is having 1000 records. Now these particular 1000 records needs to be stored in the hard disk. So how it will be stored? It will be stored in each and every block. Now consider here it is given that our hard disk has 100 blocks. So how many entries would be there per block? That is number of records divided by number of blocks. So we can say that there will be 10 entries which will be stored in each particular block. Now here we can see that in each block there would be 10 entries stored till 100 blocks. So there are 100 blocks which is present in our hard disk. So there will be 100 entries which would be made in this particular index table, and it would be having the entry for each of the first element which is present in the block. So there will be 100 entries which would be present in our index table. So you can say that each entry will point to the first record in each block. Now let's understand from this particular example that how the sparse indexing happens. So consider that this is my student table. Now in this particular student table, I have the student roll number and I have the student name. So the roll number is in a sorted manner 1, 2, 3, 4, 5, 6, and we have provided the names for all the student. Now what will happen that this particular table needs to be stored in the hard disk. So it will go ahead and store in the particular blocks which is present in the hard disk. Now in the block B1 we have 1, 2, 3. In the block B2 we have 4, 5 and 6. So per block we have 3 records which is stored in this particular hard disk. So how we can create the index table? So what we will do is first we will choose roll number as the index column. So we have choose roll number as the index column. Now we need to provide the search key, that is basically the roll number which is present here. So in sparse index what we do is we don't go ahead and provide the entry for each and every row which is present in our table. What we do is we choose the first element of the block and then we go ahead and provide the entry for that first element. So first entry would be 1, and then we will choose the first entry which is present in block B2, so that would be 4. So we have provided the roll number as the search key, and here we have provided 1 and 4. Now we need to provide the access or the data reference where that particular data is stored. So we'll provide the block B1 here, as from 1 to 3 all the data is stored in block B1, and then here we will provide block B2 as from 4 to 6 all the entries present in block B2. So this is how we create the sparse index. So how many entries could be there in the sparse index? So it is equal to the number of blocks which is present. So here you can see that there are 2 blocks which are present, so there are 2 entries which is present in the sparse index table. If there were 10 blocks present, there would be 10 entries which would be present in my sparse index table. So it is equal to the number of blocks the hard disk is having. So how sparse indexing actually works? So first is primary index. Sparse indexes are oftenly used with the primary index where the table is sorted on the indexed column. The sparse index only includes an entry for the first record of each block or page. So it only includes the entry for the first row of each block and page, and it is usually done on the primary key of that particular table, so that whenever we index the primary key, that will be always sorted and we can easily find any data value which we are searching for. Now the second thing is searching. So when the searching for a specific value, the database uses the sparse index to quickly locate the block where the record might reside. It then searches within the block to find the exact record. So how searching in the index table happens is, consider I want to search for an entry where the roll number is 3. So I want the details of the student whose roll number is 3. So what it will do is, it will first come to the index table. So it will go to the index table or the sparse index which is present. It will quickly locate the block where we can find 3. So here the search key is 1, here the search key is 4. So 3 would be lying in this particular search key. So we'll go to block B1. We'll go to block B1 here. We will pick that particular block and have it in our memory. And in our memory, we will go and search for this particular block B1 one by one. So there is 1, 2 and 3. Once we have got 3, we will take that and we will return that into our final result. So this is how the searching happens. So here you can see that we only need to search for one specific block. Earlier we were searching for different blocks. So the time complexity has also decreased. So although sparse index is helping us to execute our queries faster and get the results in faster duration of time, minimizing the disk access, there are some disadvantages which is present for the sparse index. Now what are these? So first is additional IO operations is involved. So after using the index to find the correct block, an additional search within the block is required to find the specific record. So when we are searching for a specific key, consider I am searching for roll number 3. If I am going to the index table, I am searching the index table. Wherever I am finding the search key, I am going to the data reference there, and then I am doing a search on the block which is present. So here you can see that there is an additional search which I need to do for that particular block. So because of this additional search, there is additional IO operations which is involved. Now the second thing is less efficient for random access. So if queries often need to retrieve random non-sequential record, a dense index might be more efficient. So whenever we want to do some searches in a set of data which is unordered, then we use the dense indexes. Sparse indexes can't be used there, because sparse index generally works on an ordered set of data, because here we are only providing the entry for the first element which is present in our block, right? So here we can't provide any non-sequential or non-ordered data. So whenever we want to perform any retrieval on a non-sequential or non-ordered data, we use the dense index, because dense index has entry for each and every record which is present in these particular blocks or in this particular table. So in that case, we can do any random access for a particular data item. So coming to the use cases, primary indexing on large tables. So whenever we want to perform any primary indexing on large tables where the data is mostly sequential stored, we can use the sparse index, because the sparse index helps us to fetch our queries in lesser duration of time rather than going to each and every block one by one and searching for data. It's better to go to the index table of the sparse index and then search for the data and go to the pointer and fetch that particular value. So now second one is range queries. So sparse indexes can be effected for a range queries where the query needs to retrieve a range of records rather than a single record. So consider if you want to search for a specific range of record, consider you want all the values or all the roll numbers between roll number 1 to roll number 6. So what you can do is, whenever you are performing any range queries, you can use sparse index, because here you only need to go to 2 rows or you need to only do 2 search operations, right? So here you can see that how fastly you can get a group of data or a range of data when you are using the sparse index. Now coming to dense index. So a dense index is a type of indexing technique used in databases where there is an index entry for each and every record which is present in our data file. This means that the index contains all the search keys and corresponding pointers or addresses to the actual data records, making it highly efficient for direct lookup. So whenever you want to search for any random value in a non-ordered data, you can just go to the dense index, because dense index has entry for each and every record which is present in the table. So you can just do a direct lookup from there. So it is used when we have an unordered data set. So whenever you want to make an indexing in a non-primary key column where the values are also not unique, the data is also unordered, you can use the dense index. Now consider a table with 1000 rows. Now you create a dense index on a non-primary key column, so it can have duplicate values. So the dense index will be having number of non-key unique records, each pointing to a specific row in a table. So consider that there is a non-key column on which you are providing the dense index, and it has some repetitive values, 18, 18, 18, 19, 19, 20, 20. So in the dense index, the number of entries would be equal to number of unique non-key records. So all the number of unique non-key records would be having an entry in the dense index table. So this is how the entries would be made when there is duplicate data set which is present. These are often useful in scenarios where random access to individual records is quite frequent. So whenever we want to do a random access to individual records, we can use this dense index. So here you can see that again we have the student table, and now we are providing indexing on the basis of column, that is age. So since age is a non-primary key column, we can expect some duplicate values which would be present in this particular age column, and here are the names of all the students. So now all these particular data are present in the hard disk, so it will be divided into the blocks. So each block would be having 3 rows. So B1 would be having 18, 18, 19, and then B2 would be having 20, 20, 21. So all 3 records are placed in one block, and these 3 records are placed in another block. Now how we will make the index table? So as I told, that index table would be having entries equal to the number of unique non-key columns. So here are the unique values: 18, then 19, then 20 and 21. So the search key or the indexed column on which we are making the indexing, that is age, would be having 18, 19, 20 and 21, and then we will provide the block pointer. So first search key is 18. So where 18 is present here, 18 is present here, and only block B1. So we'll provide B1 for 18. Now coming to 19, so 19 is present in block B1, so again we'll be given block B1. Then 20 is present in block B2 two times, so we can provide B2 here. And then 21, which is present in block B2, so we'll provide B2 here. So here you can see that the number of entries which is present in the dense index is equal to number of blocks unique non-key records. So unique non-key records are present in this search key in the dense index table. Now how a dense indexing works. So in a dense index, each index entry includes, first is the search key, the value of the indexed column. The second one is a pointer or address to the actual record in the data file. So where this particular actual record is stored, this particular pointer tells us. Now when a query searches for a specific value, the database uses the dense index to quickly locate the corresponding record. Now consider I want the details of all the students whose age is equal to 18. Now although age is a non-primary key attribute, but since we have indexed this particular column age, it will give me the faster results. So it will come to this particular index table, which is a dense index. It will search for 18. It has got 18. Now it will go to the block B1. It will go to the block B1. It will search in that particular block B1. Wherever it fetches 18, it will take that particular data and it will return that in the final result. So in this way, we can search for any random data which is present in our table using the dense indexing. Now, what are the disadvantages of dense indexing? So it requires significant storage space because it maintains an entry for every record in the table. So in sparse indexing, we were only storing the entry for each first element in the block, but here we are storing the entry for each record which is present in our table. Consider here also we are storing only for non-unique record, but again there are so many records which is getting stored here, right? So the storage is very intensive. Now coming to the next point, that is maintenance overhead is there. So inserting, updating or deleting records require updating the dense index, which can be costly in terms of performance, especially for large tables. So consider in this particular table, now Raghu has turned 20. So we have updated the value of Raghu's age to 20 here, but we need to update it that in the index table as well, because now it will be pointing to a wrong block pointer. Because of this, these particular operations are very expensive. So what are the use cases of dense indexing? First is primary indexing. Dense indexes are oftenly used for primary indexing when the table is small to medium size and quick access to individual records is required. So whenever we want a quick access to individual records, we can use this dense index because it has entry for each and every record which is present in our table. Now second one is exact matching queries. So it is ideal for the situation where the queries frequently request for individual records based on an exact key match. So whenever we want an exact key match that fetch the value of a person whose age is equal to 18. So whenever we were using sparse index, we used to provide the first element of the block, so we need to search for that particular block where the exact entry can happen. But in dense index, we can find the exact entry or exact record in the dense search key itself, so we can find the exact record very easily. Now whenever a query is run, the database engine checks the index to find the pointers to the row that contains desired data. It then retrieves this rows directly without scanning the entire table. So this is our index table. It goes ahead and searches in our index table. Once it searches in our index table, it goes to the block pointer where the data will be present. It fetches the data and it gives us the final result. Rather than going to each and every block one by one, we are reducing the block access which we are doing in our hard disk. Now how indexing works? So it takes a search key as an input and then returns a collection of all the matching records. So consider if I am searching for all the people who are having age 18, there could be multiple people who are having age as 18. So it will search for all the records where the age is 18 and it will return a collection of all the records. Now in index there are two columns. The first one is the one which stores a duplicate of key attribute or a non-key attribute, that is a search key. So search key can either be a key attribute or a non-key attribute in our given table. Now from the table, while the second one stores the pointer which holds the disk block address of the corresponding key value. So in corresponding to each and every search key, there are some block pointers which is stored. Now these particular block pointers point to the address that in our hard disk where this particular data for which we are searching is stored. So in the hard disk, all the data is stored in the form of blocks and we can provide the address of this particular block in this particular column. So we have learned about indexing. Let's learn about types of indexing. So there are mainly three types of indexing. First one is clustered index, second one is multi-level indexing, and third one is non-clustered index. Now in clustered index, we have two types of indexing. First one is primary indexing and second one is clustering indexing. Now when primary indexing happens, so when the key on which we are indexing is a primary key and the order of the data is sorted, we call it as primary index. It basically follows the sparse indexing methods. Now coming to clustering index, So when the key on which we are indexing is a non-key attribute, but the order or the data is sorted, we say that clustering index is present, and this we follow the dense indexing since there is a non-key attribute which is involved but the order is sorted. Now coming to the multi-level indexing. So whenever there is one more level of indexing in the index table, we use inner and outer indexes. So whenever our database is so large or so huge, the index table also becomes bombarded with entries. So we perform one more level of indexing there. We'll be learning about multi-level indexing in the next couple of slides. So it is mostly used for large files. Now coming to the non-clustered index, that is secondary index. So whenever the key is a non-key or a key attribute and the order is unsorted, so the data is not in a sorted manner and the key on which we are performing the indexing can be a non-key or key attribute, follow the secondary index there, and we follow the dense indexing as an indexing method there. Now let's learn about each and every type in more depth. Distinguish the indexing based on the keys and non-key attribute. Now what they are exactly. So key attribute is a unique identifier for each record. It is oftenly used to distinguish one record from another. So whenever we want to distinguish one record from another record, consider if there are two records R1 and R2, there is an attribute which is present for R1 and R2 which can help me to distinguish between those two records. So that is called as key attribute. Now coming to the non-key attribute, so all the other data in the record besides the key, so all the other columns or all the other attributes beside the key attribute is called as non-key attribute. Now what is the single level indexing and multi-level indexing? So whenever there is only one index table involved, we can say that there is a single level of indexing present. But whenever there are multiple index table involved like inner index, outer index, we can call as multi-level indexing. So single level indexing is straightforward and works well for a smaller databases, offering a direct approach to speeding up query performance. Whereas multi-level indexing is more complex but necessary for larger databases as it effectively manages large indexes by creating an additional layer of indexing, thereby improving the data retrieval times. So here an additional layer of indexing is created in multi-level indexing because the databases is very large and have a lot of data which is present in that. So let's learn about primary index. It enhances the efficiency of retrieving records by using their primary key values. So here we use the primary key values of the given records. Now it establishes an index structure that associates primary key values with the disk block address. Now here this is the index structure where we provide the primary key of this particular table. Consider this is roll number, so roll number would be an index, and here we provide the pointers to that particular data where it is stored in this particular hard disk or in this particular blocks. Now this index is composed of a sorted list of primary key values with their corresponding disk block address. So this is a sorted data of the primary key values and their disk block address. Now thereby accelerating the data retrieval by reducing the search time. It is specially beneficial for queries based on primary keys. It is done on sorted data. So whenever our data is sorted and we have primary key which is present in our table, and whenever we want to index our primary key, we use this primary index. Now here you can see that there is a search key and the data reference which is basically the data pointer to the block which is present here, and here we have a student table. Now in this particular student table, roll number is acting as a primary key. So this particular data would be feeded in our hard disk. So this particular table will be present in our disk. For the first 3 records it will be stored in block B1. For the next 3 records it will be stored in block B2. And here we have provided the roll number, the name, and different set of data which is present in our disk. Now here whenever we are making the index table, as I told that whenever we are using the sparse index, we only provide the first element of the given block in our index search key. So here we are providing 1 for block B1 and here we are providing 4 for block B2. So here we have provided the address for that particular blocks. Now here sparse index, the number of records in the index file is equal to the number of blocks. So here we have 2 blocks, so there are 2 entries which are present in our index table. So this is our index table which creates an index structure that maps primary key values to the disk block address. So it maps the primary key values to their corresponding disk block address. Let's understand from an example. In a user table with user ID column as a primary key. So here user ID column is the primary key. A primary index on user ID can allow for quick retrieval of user records when you know the user ID. So whenever we know the user ID, we don't need to go ahead and search for each and every block for that particular user ID. Rather what we will do is we will go to the index table, and when we know the user ID, we'll search in the search key, and wherever we find the block pointer corresponding to that, we'll go to that particular block and bring that block in our memory and search for that particular values and get the details easily. So primary index ensures that the database can immediately locate the row associated with a given user ID, making operations like select, update, delete highly efficient. So it makes these operations like select, update and delete when we know the user ID highly efficient. Now the next one in clustered index is clustering index. So clustering index is generally done on a non-key attribute. So whenever there is a non-key attribute as well as the data is sorted, we use the clustered index. So the data in the table is typically ordered according to the order defined by the cluster index. Mostly each index entry points directly to a row. It is mostly used whenever we are grouping the data. It is physically ordering the records in a table based on the index column. So what happens here is ki consider this is the column age, which is a non-key attribute, but the data which is present in our age is sorted. We can use this cluster index. Now in this particular non-key attribute, we can see that the data is sorted and age is a non-key attribute. Because of that, we can see that there are some duplicate data which is also present. Now this particular table will be present in a hard disk. So first 3 records would be present in block B1 and then the next 3 records will be present in block B2. Now here we have provided the age on which we are doing the indexing, which is a non-key attribute. So age here is 18, 18, 19, 20, 20, 21. Now here we'll be doing a dense indexing because here we can see that the data is sorted but there is a duplicate data as well as it is a non-key attribute. So we need to do a dense indexing here. Now in the dense indexing, what we will do is we will only provide the entry for the unique non-key attributes. We won't go ahead and provide entry for 18 2 times, 19 1 time, again 20 2 times. We'll only provide for the unique entry. So number of records in the index file will be equal to number of blocks of unique non-key records. So here we have gone to the search key. Here we have provided the entry for 18, then 19, then 20 and then 21, and here we have provided the block pointers for that particular data which is present in our hard disk. So whenever we want to search based on a non-key column, consider that I want the details of all my students whose age is 19. So what it will do is it will go to the index table, it will search for the search key 19, it has found the 19. Now it will go to the block pointer where it is present, that is B1. Now it will go to B1, will search for the record 19 and then it will return either a single or the collection of data which is present in our hard disk, or you can say in our blocks. So let's understand from an example for a cluster index. So consider that there is an employee table. If you need to produce list of employees ordered by last name, creating a clustered index on last name can make the queries faster. So whenever there is a non-key attribute, there would be some duplication, and whenever we want to perform any group by operation or order by operation based on a non-key attribute, we can use this cluster index because it can make the queries run faster. Now cluster index keeps the rows in the last name order, reducing the need for the database to perform additional sorting when executing the queries. Now we have performed the indexing on the last name. So what it will do is it will order the last name which will be present in our index table. So we don't need to perform any additional sorting operations. We can use the index table and we can perform the group by or the order by clauses there. Now coming to the multi-level index. So multi-level index is an advanced indexing technique used in database management system to manage large indexes more efficiently. So whenever there are some large indexes or there are large data which is stored in our index table, we use this multi-level indexing. Now when a single level index becomes too large to fit into the memory, multi-level indexing help us in breaking down index into multiple levels. So it breaks down this particular index into multiple levels. So there is an outer index and there is an inner index which is present. So it reduces the number of disk IO operations needed to search through the index. What are the levels in the multi-level indexing? First one is the first level, that is primary index. The first level is the original index where each entry points to a block of data or a page in the table. So the first level consists of original index where each entry points to a block of data or page in the table. Now coming to the second level, that is secondary index. So if the first level index is too large to fit in the memory, a second level index is introduced or created. This index points to the block of first level index, effectively indexing the index itself. So consider that this is my index table. What will happen that there will be one more level of indexing which will happen. Now this particular index table will be having some of the entries of this particular index table because here the data is sorted and there is a key attribute also present. So we'll be following a sparse index and some of the entries will be stored here. So here you can see that we are having an employee table. Now in this particular employee table we have employee ID and the different data of that particular employee. Now here the employee IDs are given and corresponding blocks of them are given here. Now we make the index table. In that particular index table we are indexing on the basis of EID. So we'll provide this EID in the index table and then we'll provide the pointer to that particular address where this data is stored. So we'll be providing the EID as E101, basically the first element of the block, and then we'll providing the block pointer. Now coming to this block, the first element is E151, so we'll provide B2 and E151. In the same way we'll provide for all the entries which is present in these blocks. So here you can see that our index table is getting bombarded with a lot of entries, and here I have only considered some of the data. In real world there are lakh and crore of data, right? So what we will do is we'll create an outer index, and in this particular outer index what we will do is we'll group the data which is present in this index table, and then for that particular group we'll provide the EID and here the pointer to that particular group. So we have divided it into groups and we have provided the first element of the group, that is E101, then E201 and then E301. So for all these particular groups we have provided an entry, and here we have provided a pointer to that particular entry. So here you can see that we have introduced a new level of indexing and we have indexed the index table itself because the data was so large. So this is how the multi-level indexing works. Now coming to secondary indexing. So secondary indexing speeds up the searches for non-key columns in a database. Unlike primary indexing which uses the primary key, secondary indexing focuses on other columns. So whenever we have other columns apart from primary key, we can use this secondary indexing. Now it creates an index that maps column values to location where the records are stored, making it faster to find specific records without scanning the entire table. Now in the secondary index, we basically work on the key as well as the non-key attribute, and the data is always unsorted. So whenever we want to work on a data which is unsorted and it can either be a key or non-key attribute, we use the secondary index. So the data is mostly unsorted and it can be performed on both key and non-key attributes. Now here key attribute doesn't only mean the primary key. There are multiple keys which are present in our table. Consider primary key, candidate key, super key. So don't ever consider that if there is a key attribute, it is always a primary key. It can be other attributes as well which is holding some unique values because of which we can find some data. Now the secondary index will be having two cases. The case one is when the search key is a key attribute and data is unsorted, and second is when the search key is a non-key attribute and the data is also unsorted. So let's learn about the first case when the search key is a key attribute and the data is unsorted. So here we have selected age, which is a non-key attribute, and the data is also unsorted. Here you can see 18, 20, then 45, 67, 68, then 22, 24, 30. So here the data is also unsorted and it is also a non-key attribute. So it is now stored in the blocks which is present in our hard disk. Let's understand it how the indexing will be done in this particular case. So here we can see that age is having an unsorted data, so we can use a dense index, and in this particular dense index what we will do is we will provide an entry for each and every record which is present in our table. We have to just make sure that that entry should be unique. There shouldn't be duplicate entry which should be present in our index table. There should be only unique entries which should be present. So we'll go ahead and provide these particular entries in our index table. But the best thing about the index table is that the index table is always sorted. So it will go ahead and it will enter the data in a sorted manner. So search key will be present in a sorted manner, and then there will be a data reference or the block pointers to that particular search key. So here we have followed a dense indexing where the number of records in the index file is equal to number of blocks of unique key records which is present in this particular case. Now coming to the next case when the search key is non-key attribute and the data is unsorted. Now here age is a non-key attribute as well as the data is also unsorted. So here you can see what is happening. Age is 18, 18, then 20, then 67, then 22, then 22, 24 and 30. Here you can see that the data is also unsorted. There are some duplicate datas and it is a non-key attribute. Now in this case how the indexing will happen. So here we can see that the 22 is happening in block pointer B1 as well as in B2. So how we will mention that in our index table. So what we will do is first we will provide the entry for each and every unique non-key record in our index table, and whenever we find that for a unique non-key record there is some entry which is present in B1, B2 or different blocks, what we will do is we'll represent it in the form of a linked list. So what we will do is in the data reference column we'll provide B1 and then the next occurrence of this particular 22 in this particular block, that is B2. So we'll provide it in a linked list manner or in a linked list fashion. So this is how we provide the search key, which is always sorted in our index table, and this is how we provide the data reference. So here in the DES indexing, the number of records in the index file will be equal to the number of blocks of unique non-key records. Here we have discussed about almost all the types of cases when we have a key data but the data is unsorted, when we have a key data but the data is sorted, when we have a non-key data but the data is unsorted, when we have a non-key data but the data is sorted. So we have discussed on all these cases. Now we will be discussing on how we can create indexes in our databases. So how to create indexes? So we can create indexing based on one column or multiple columns. So let's see. First we'll see that how we can create non-cluster indexes, basically secondary indexes. So when we want to create on one column, so we give this command create index followed by a name which we provide to the index, and then we provide on, then the table on which we are creating the index, and then the column on which we are creating the index. So this is for one column. On multiple column we give the same command create index followed by index name, then on, table name, and then we provide the different columns in comma separated way. So this is how we create in non-clustered indexes. Now when we want to remove an index, we give this command drop index, then the index name, and then we provide on, and then we provide the table name. Now coming to the clustered index, so it automatically gets created with the primary key. MySQL does not support explicit creation of additional clustered indexes. So MySQL does not support any additional creation of clustered indexes. It automatically creates with the primary key itself. So before starting with B and B plus trees, let's just understand that why do we even need to learn about them. So clustered and non-clustered indexes are concepts that describe that how the data is stored and accessed in our database. So it tells us that how the data is stored and how we can access the data. But B trees and B plus trees are the data structure that actually implement these indexes. So the implementation of these indexes are done using B and B plus trees. So knowing B trees gives you insight into how these indexes work under the hood. So it helps us to tell about the implementation of these indexes. Now understanding B trees helps you to understand that why certain queries perform very well and poorly based on the structure of the index. So based on the structure of the index, we can determine that why a given query is performing very poor or very great. So for example, how a B tree or balanced nature affects search times, or why range queries are efficient with B tree indexes. So the balanced nature of B trees help us to get our data retrieval very fast, and it also helps us to search for the range queries. Now B trees provide the balanced, efficient structure that makes these type of indexes performant, ensuring that the operations like search, insert, delete and update are done in logarithmic time. So all the CRUD operations like create, read, update and delete are performed in logarithmic time whenever we use B tree data structures as part of our indexes implementation. So these makes B tree indexing crucial for optimizing database queries, whether in a clustered or non-clustered index scenario. So it really helps us to get all those CRUD operations performed in the logarithmic time, which is such a great time complexity, and we can get our data very fast. Now what is this B trees? So B trees is also called as a MV tree, where M defines the order of the tree. So we'll be learning about order of the tree in next set of slides. For now you can just understand that B tree also is called as MV tree, where M represents the order of the tree. So B tree are self-balancing tree data structure that maintains sorted data and allows searches, sequential access, insertion and deletion in logarithmic type. So all the CRUD operations are performed in a logarithmic time. Also all leaf nodes are at the same level in the B trees. So all the leaf node or the last node are at the same level in the B trees. Now in B tree you can minimum have 2 children and maximum x children, where x is the order of the given tree. Order is also represented using M, but here I am using x for reference. So x children. Now B tree is a generalization of a binary search tree. So if you don't know about binary search tree, I'll suggest you to go ahead and have a look on what is a binary search tree, because if you have a basic concept on binary search tree, B tree and B plus tree would be really easy to understand. Now in binary search tree, every node can have at most 2 children. That is, if this is can either have 0 children, 1 children or 2 children. In the B trees we can have at max of x, or you can say m children, that is the order of the tree. Also here there would be only one key which would be present in each node, but here there could be multiple keys which is present in our nodes. Now let's learn about the structure of a B tree. So the first one is node. A B tree is composed of nodes, each containing keys and pointers to the child nodes. So this is a node which contains a key as well as block pointers which references to the child nodes. So these are the child nodes and these are the block pointers which references to the child nodes. Along with the key, we also have a data pointer. Now what is a data pointer? So data pointer or record pointer is the one where the record is present in the secondary memory. So data pointer or record pointer help us to know at what particular location our record is present in the secondary memory or the disk. Now the keys within a node are sorted in ascending order. So all the keys which are present within a node are sorted in ascending order. Now root, internal nodes and leaves. So the root node is the topmost node in the tree. So the topmost node in the tree is called as a root node. Now coming to the second one, that is internal nodes. So internal nodes contain keys and the child pointers. So these are the internal nodes after the root nodes which contains the key as well as the child pointers, or you can say the block pointers. So these are the block pointers. Now coming to the third one, that is leaf node. So leaf node contains key and possibly pointers to the record of other data. So this leaf node also contains key and the block pointers, and these particular block pointers, when there are no further nodes, it points to the null. So these are the keys which are present here and it points to the null. Along with the keys, we have a data pointer which tells us where the record is present in our secondary memory, or you can say disk. Now in indexing, each key in a B tree node typically represents a value or range of values, and associated pointer directs to a data block where the record is present corresponding to the key can be found. So for example, in a database, the key might be the value in a column and the pointer might be direct location to the row or a set of rows in a given table. So here we can see that all the nodes are having the same structure. They are having key, they are having the data pointer associated to the key, then they have a block pointer which corresponds to the address of their children's, and here it is the root node. After the root node, all the nodes are the internal nodes, and then at the last one we have the leaf node which also has key and data pointer. Now a B tree of order x can have the maximum number of children a B tree can have is x, that is the order of the tree. So the maximum number of children any node can have is the x, that is the order of the tree. Now coming to the maximum number of keys. So the maximum number of keys for every node is x minus 1. Now why it is x minus 1? So consider here the keys are provided k1 and k2, and here we have provided the block pointers. So at max I am saying that this particular tree can have only 3 children. So we'll have 3 block pointers, 1, 2 and 3, and here you can see that we have only provided 2 keys because there is 3 block pointers. So we can say the number of block pointer is the maximum number of children a key can have, or the order of the key, and the number of keys is order minus 1, that is x minus 1. Now coming to the minimum number of keys. So the root node can have minimum 1 key. The other nodes apart from root can have ceiling of m by 2 minus 1. Now what is this ceiling? So ceiling tells us the upper value. So consider if I am dividing 8 by 2. So it is giving me 4. But consider I am dividing 9 by 2. It is giving me 4.5. So it will take the upper value of 4.5, that is 5, and 5 minus 1, it will give me 4. So whenever we want to find the minimum number of keys for root node, it will always be 1. For other nodes, it would be ceiling of m by 2 minus 1. Now what are the minimum number of children? For the root node, we can have at most 2 children. For the leaf node, we won't be having any children because leaf node is the last node in the tree. And coming to the internal node, we will be having ceiling of m by 2. This is the minimum number of children internal node can have. Leaf node will be having 0 and root node will be having 2. The minimum number of keys in the root node would be 1. That is, there would be only 1 minimum number of key. The other nodes can have ceiling of m by 2 minus 1. The maximum number of keys every node can have is x minus 1, where x is the order of the. So insertion in B tree always happens from the leaf node. So you have to make sure that whenever you are inserting any value in the B tree, it always happens from the leaf node. It doesn't happen from the root node. So we have to insert the value only from the leaf node. If it overflows the value, then we push it to the internal nodes or the root node, but the value insertion start from the leaf node itself. So let's take a node of a binary tree. Now in this particular node, we will be having a block pointer which contains the reference to the child node. Then we have a key, and then we have a data pointer which contains the reference for the record in the disk. So what we will do is, this is the node. Now in this particular node, how many block pointers can be there? So the block pointers is equal to the order of the tree. So at max, the order of the tree is considered 3, so there will be 3 block pointers. So here there will be a block pointer BP1, then there will be a key K1 D1, then there will be again a block pointer BP2, then there will be a key K2 D2, and then so on. There will be multiple block pointers as well as key and data pointers. Now consider that if someone provides you the block size, the block pointer size and data pointer size, how you can find the order of that particular tree. So this is the block size, like this particular block has a size, so that is called as a block size. Now this is the block pointer size and this is the key as well as the data pointer size. You can derive the formula for the same. So here M is the order of the tree and the number of block pointers depends on the order of the tree. If the order of the tree is 3, then there will be 3 block pointers. If the order of the tree is 5, there will be 5 block pointers. So we will multiply M with PB, where M is the order of the tree and PB is the block pointer size. Now coming to the key as well as data pointer. Now key and data pointer are always 1 less than the order of the tree, because there are some block pointers and there are some keys and data pointers, and keys and data pointers are always 1 less than the block pointer. So it will be M minus 1, that is order minus 1, into K stands for key and PD stands for the data pointer size. So we will add this key and data pointer size together and then we will multiply it with M minus 1, that is order minus 1, and that should be less than the block size. So here the number of keys a node with M children can have maximum of M minus 1 keys. Number of block pointers, each node has M block pointers to the child node. Number of data pointers, each key has an associated data pointer, so there are M minus 1 data pointers. So the data pointers and keys are always M minus 1, that is 1 less than the block pointers, and the block pointers are always the maximum of the order of the tree, that is X or M, that is the order of the tree. Now let's say you have a block size B of 1024 bytes, you have a block pointer size PB as 8 bytes, you have a data pointer size PD as 12 bytes, and you have a key size K as 16 bytes. Find the order of the tree. So you have to find the order of the tree. So we'll come to that formula where we will multiply order of the tree with the block pointer size, that is PB, that is 8. Then we will subtract 1 from the order, because the key pointers and data pointers are always 1 less than the block pointers. So that is M minus 1. Then we will add the key pointer as well as the data pointer, that is 16 plus 12, and that is always less than and equal to block size, that is 1024. So here we can find the order of the tree is 29. So in this way we can find the order of the tree when all these values are provided to us. So what are the steps to insert values into the binary tree? So first one is start at the root and recursively move down to the tree to find the appropriate leaf node where the new value should be inserted. So as I told, that insertion in the binary tree always happens from the leaf node. So we have to find the leaf node where we can insert the value. Now second one is insert the value into the leaf node in a sorted order. So we have to insert the value into our leaf node in a sorted order. If the leaf node has fewer than the maximum allowed keys, that is order minus 1, this step is simple. So consider that if I have to insert 1, 2 and 3 and this is my leaf node. Now this particular leaf node doesn't have any data at all. So what I'll do is insert 1 and then I'll insert 2. But consider the order of this particular tree is 3. So the maximum number of keys which can be inserted is M minus 1, that is order minus 1. So 3 minus 1 is 2. So we can only insert 2 keys at max in the leaf node. But consider that if I have to insert 3 also, then how the insertion will happen? So if the leaf node contains the maximum number of keys after the insertion, it causes an overflow. So what we have to do is we have to split the nodes. So divide the nodes into 2 nodes. The middle key median is pushed up to the parent node. So what we'll do is we'll find the median of this, that would be n by 2. So we'll find n by 2 and we'll find that 2 is the median node. So it will be pushed to the parent node, and then once it's pushed to the parent node, it can hold 2 elements. To the left of this particular parent node, we will be having 1. To the right of this particular parent node, we will be having 3. So this will be a lesser value than 2 and this will be a greater value than the parent node. So the left half or the original node stay in the place while the right half forms a new node. So insert the median into the parent. If the parent node also overflows after this insertion, recursively split the parent node and propagate the median up the tree. So the fourth one is if the root node overflows. So consider the node in which I am inserting the data, and because of this I am pushing the data to my parent node. Like whenever I am inserting the data into my leaf node, if the leaf node is overflowing, I am inserting or pushing the data into my parent node. But consider that the parent node also overflows and the parent node is the root node. Then what we should do in that case? So which can happen if it already has the maximum number of keys, split it into two nodes and the median becomes the new root. So what you have to do is you have to split it again into the two nodes and then the medium becomes the new root. So we can say that this increases the height of the B tree by 1. So this will increase the height of the B tree because earlier we had only two particular levels, but now we have 3 levels. So let's see that how we can create a B tree of a given order and how we can do the insertion of the values into our B tree. So create a B tree of order 3 and insert values from 1, 4, 6, 8, 10, 12, 14 and 16. So the maximum number of children a tree can have is equal to the number of block pointers, which is equal to the order of the tree, that is order of the tree is 3. Now coming to the maximum number of keys a given node can have, that is order minus 1, that is 3 minus 1, so 2. So the maximum number of keys a node can have here is 2 and the maximum number of children a node can have is 3. So insertion in B tree happens from the leaf node and the values are also inserted in sorted order. So the element in the left of the root would be having less than the root and the element in the right of the root would be having greater than root. So if this is the root and any element which is inserted in the left of the root would be having lesser value than the root and the one which is inserted into the right of the root would be having a larger value than the root. So step 1. Start at the root and recursively move down to the tree to find the appropriate leaf node where the new value should be inserted. But this is a new tree which we are creating, so we will be starting from the leaf node. So we have to insert the value into the leaf node in sorted order. So the first value is 1, I've inserted 1. The second value is 4, I have inserted 4. So if the leaf node has fewer than the maximum allowed keys, that is order minus 1, this step is simple. So this step is simple. We have inserted 1, we have inserted 4. But here it is told that the maximum number of keys a node can have is only 2. Now we have to insert 6. So how can we insert 6? So what we will do is, in the step 2, if the leaf node contains maximum number of keys after the insertion, it causes an overflow. So split the nodes, divide the nodes into two nodes. The middle key, that is median, is pushed up to the parent node. The left half of the original node stays in the place while the right half forms a new node. So 1 and 4 is already inserted in my node. Now I have to insert 6. But here the maximum number of keys a node can have is 2. So I have to insert 6. So what I'll do is I'll find the medium including the 6. So that would be n by 2 because the number is odd. So the median would be 4. So what I'll do, I'll push 4 to the parent node and then 4 will be created as a parent node, and in the left of 4 I'll be having 1 and in the right of 4 I'll be having 6. So this is how we split the node and we push the median of the node to the parent node. So here you can see that we have created a new node, that is a parent node. Now in this node the left of 4 is having 1 and the right of 4 is having 6 because this value should always be less than the parent node and this value should be greater than the parent node. Whenever there is a overflowing which happens, push the median of the node to the parent node. Now we have inserted the median into the parent node. If the parent node also overflows after this insertion, recursively split the parent node and propagate the medium up the tree. But here the parent node has not overflowed. So now we have to follow the step 2 again to insert other elements. So we have inserted 1, we have inserted 4, we have inserted 6. Now we have to insert 8. 8 is greater than 4, so it will come into the right of 4, so we'll insert it here. After 6, 8 is inserted. Now we have to insert 10. Now again the same situation is coming where we are overflowing the data, so because of which what we'll do is, so we'll push the median to the parent node and we'll create a new node in the right to insert 10 as 10 is greater than 8. So here we have pushed it to the parent node and here we have inserted 10. So to the left of 4 we are having 1, to the right of 4 we are having 6, to the right of 8 we are having 10. Now we have to insert 12. So we can insert 12 to the right of the 8 because it is greater than 8, so we have inserted 12 as well. Now we have to insert 14, but how we will insert 14? Here the data is already overflowing, so we'll send the median to the parent node. But now parent node is also overflowing, so we have to push the median element of the parent node to the root node. So what we will do is, we have pushed 8 here. Now to the left of 8 we are having 4. Now 4 is having 1 and 6. To the right of 8 we are having 12. Now we are having 10 as the left of 12 and 14 as the right of 12. So let's understand from here what we have done is, here we have pushed 12 to one step above. So here 12 is here and 4 is here. Now here, since there were 3 elements again which was overflowing, so we have pushed the median 8 to one more above node, that is a parent node. So here we have pushed 8 here. Now to the left of 8 we are having 4, to the right of 8 we are having 12, to the left of 4 we are having 1, to the right of 4 we are having 6, to the left of 12 we are having 10, and to the right of 12 we are having 14. So in step 3, if root node overflows, which can happen if it already has a maximum number of keys, split it into 2 nodes and the median becomes the new root. This increases the height of the binary tree by 1. So here we can see that the height of binary tree was having only 2 levels, 0 and 1, but here the height of tree has been increased. So this is how you can do an insertion in our binary trees. Let's learn about the deletion in the binary key. So in the insertion, we were saying the maximum number of keys a given node can hold. But in the deletion, we need to see the minimum number of keys a given node should have. Because consider if I delete all the values which is present in our node, so it will be violating the binary key rules. So we have to search for the minimum number of keys which a node can have. So here we are considering a binary tree of order 4. So the minimum number of keys is ceil of m by 2 minus 1, that is 4 by 2 minus 1, that is 2 minus 1, that is 1 key. So when the order is 4, the minimum number of keys a node can have is 1 key. So let's start. So the step 1 is begin at the root and recursively move down the tree to find the node that contains the key to be deleted. So we'll start from root and then we will search for the key which needs to be deleted. Now the step 2 is consider the case where the key is a leaf node. So we have to consider a case where we have to delete a key which is present in a leaf node. So first one is simply remove the key from the leaf node. So what we have to do is first we have to search for the key which we need to delete, that is 10. So we'll come here and we'll see the root is 40 and 50. So the key, that is 10, will be less than 40. So we'll come in the left and here we have found the 10. Now here what we have to do is we have to delete 10, but we have to make sure that the minimum number of keys remains 1. So is the minimum number of key remaining 1 after deleting 10? Yes, so we can simply delete 10. So if the node still has the minimum required number of keys, the deletion is complete. So the deletion is complete because it still has the minimum number of keys which is required. Now coming to the case 2 where the key is in the leaf node, but there could be a possibility that if I am deleting that particular key, the node is having less than the minimum number of required keys. So consider here I am deleting 20. So if the deletion causes the node to have fewer than the minimum number of keys, proceed to the borrowing or the merging step. So we have to follow a borrowing or the merging step. Now how we can follow that? So here I have to delete 20, right? But if I delete 20, the minimum number of key which is needed is 1. That would be violated. So what I'll do is, if the node has a sibling with more than minimum number of keys, you can borrow a key from the sibling. The parent key between the node and the sibling moves down to the node. Here I have to delete 20. What I'll do is I'll find the sibling, immediate sibling of 20. So there are no siblings in the left, there are some siblings in the right. Now I'll see that if the number of siblings is having more than the minimum number of keys, so the minimum number of key is 1 and the sibling is having 2 keys. So we can borrow 1 key from this particular sibling. This node A can borrow a key from node B so it can maintain the minimum number of keys. So this particular borrowing happens via the parent node. So what happens here, we are deleting something which is in the left of the parent node. So we'll be picking the smallest value from the parent node. So here it is 40 and 50. So we'll be picking 40. We will be giving 40 here. And then we will be deleting 20, and from here, since parent needs to maintain the 2 keys because it has borrowed from the sibling, not from the parent. So from the parent we will pick up the maximum value and we will go ahead and provide it here. So now it will be 4750. Here is 40 because we have deleted 20 and here it is 44. So the minimum number of keys is maintained here as well and here as well. So there is a borrow which has happened between these 2 siblings via the parent, right? Now here you would be thinking that why we are sending the smallest value here and why we are borrowing the largest value here. So here we are deleting from the left node of the parent. So left node always contains the smallest value. So from here also we will be using the smallest value so that this particular root and parent node does not have any unbalanced or unsorted way in which the data is stored. So we will give 40 here and here we will pick the largest value because here we are replacing the key from the right of this particular 40, right? So from the right of this particular 40, if we are replacing the value, we need to pick up the highest value. So we'll pick 47 and we'll put it here. Now consider another case that the key is again a leaf node, but when we are deleting a given value or a given key, it can't even borrow from the sibling because sibling also has the minimum number of key. So consider that I have to delete 40. And I can't borrow from my sibling because sibling also has the minimum number of key which is required. If I borrow from the sibling, it will be short of the key, right? So in that case, merging happens. So if borrowing is not possible, that is the sibling also has the minimum number of keys, merging the node with a sibling happens. Now the key from the parent that separates the two nodes move down into a newly merged node. If this causes the parent to have too few keys, repeat the borrowing or merging process at the parent level. So what we will do here is we will merge this 40 and 44, and from the parent node, which is a common between these two keys, that is 40 and 44, that is 47, will come down and perform in this particular merging. So it will be 40, 47 and 44, and then we can go ahead and delete 40. So what happens is merge the node with the sibling. The key from the parent that separates the two nodes move down in a newly merged node. So it will be 50, 44, 47, since we need to store our data in a sorted manner, and here it will be 52 and 59. So this is how the merging happens when the sibling doesn't have more than the minimum number of keys, and this is how borrowing happens when the sibling has more than the minimum number of keys. Now coming to the next case, when the key is an internal node. In the last case we saw about the leaf node. In this case we'll be seeing about the internal node. So here we have to delete 20. Now 20 is an internal node here. So how the deletion happens? So what we do is we replace the key with its predecessor, the largest key in the left subtree, or its successor, the smallest key in the right subtree. So here we have to delete 20, but the minimum number of keys which is required for a given node is 1. So if we delete 20, it will violate the binary tree rule. So how we can delete 20 when 20 is an internal node? So what we will do is we'll replace the key with its predecessor or successor. So we will replace it with its predecessor or successor. What is predecessor? The largest key in the left subtree. So we'll go into the left subtree and we'll find the largest key, that is 10 and 11. So we'll replace 20 with 11 and we will delete 20. Here we can replace it with 11 because the minimum number of keys which is required is 1. So here if there is 10, the minimum number criteria is matching. So delete the predecessor or successor key from the corresponding subtree. So we can delete this particular key which is a predecessor or successor to this particular 11. Now if this causes an underflow, the node has few keys, proceed to the borrowing and merging step. So if this particular causes an underflow, we have to go to that borrowing and merging step. Now consider if we have to delete 11, and 11 is the minimum number of keys a node can have is only 1, and if we delete 11 it will violate that property. So we have to do that borrowing and merging step which we discussed in the leaf node. In the same way it will happen here as well. Now let's learn about B plus tree. So a B plus tree is an extension of B tree and is commonly used in databases and file system to maintain sorted data and allow for efficient insertion, deletion and search operations. B plus tree is also a balanced tree, meaning all the leaf nodes are at the same level. So in B plus tree also all the leaf nodes are at the same level. It is a balanced tree. Basically it is an extension to the B tree. Now here I am saying that B plus tree is an extension to the B tree. Then what are the common differences between B tree and B plus tree? So the key difference between B plus tree and B tree lies in how they store the data and how the leaf nodes are structured. So there are some differences in how they store the data and how the leaf node of them are structured. So the very first one is, in B tree all the actual data or references to the data are stored in the leaf nodes and internal node only stores the key. So in B plus tree what was happening was every node was storing key, data pointer and block pointer. The block pointer points to the children, the key points to the value, and the data pointer points to the address where the record is present in our hard disk. Now in this particular B plus tree what happens is, in leaf node only we store the key and the data pointer. In other internal nodes we only store the key, not the data pointer. So only in the leaf node we store the key and the data pointer, and there is only one block pointer which is present per node which points to the next leaf node which is present in this B plus tree. So in B tree what used to happen was, there was a key, there was a data pointer, there was a block pointer, and this particular block pointer used to point to null when it was a leaf node. But in B plus tree there is key and data pointer, and then there is only one block pointer per node which points to the next node which is present in this leaf. Now coming to the next point, in a B plus tree leaf nodes are linked together in a linked list fashion. So they are linked together in a linked list fashion and they use the block pointer for the linking purpose. Now each leaf node can have only one block pointer which contains the address to the next leaf node. So this is how the leaf node looks. It has key, it has data pointer and it has block pointer which addresses to the next leaf node which is present in this this system, and it follows a linked list fashion. During inserting the value in B plus tree, a copy of the key is always stored in the leaf node. As I told that the internal nodes only have the key, it doesn't have the data pointers where that particular record is present in our disk. All the details are present in the leaf node only. So what will happen that whenever we insert any value in the B tree, the leaf node always have copy of that particular node in the leaf node in a sorted manner. So here if I am inserting 30 and 70 in the leaf node, I'll be having a copy of 30 and 70 because in the leaf node we have the data pointers. In the internal nodes we don't have any data pointers, we only have key. Now coming to the internal node. So internal node do not store data pointer, only keys and the child pointers. So in the B tree what used to happen was there was a key, there was a data pointer, and then there was a block. But here what happens is in the internal node there is only key, there is no data pointer which is present, and there are some block pointers which points to the child nodes. So this is how the internal node is designed in B plus tree. So this allows more keys to be stored in each internal node, leading to a lower height and more efficient operation. Now data pointer don't needs to be stored, so the amount of size which data pointer was consuming is reduced. So we can go ahead and insert more number of keys in B plus tree rather than B trees, and this will help us to have a less height of the tree rather than B trees. Now what is the structure of B plus tree? So the first is root node. The top node of the B plus tree which points to the first level of internal nodes or directly to the leaf nodes if the tree has only one level. So this is the root node which points to that internal nodes, and if there are only two levels of nodes which are present, then it points to the leaf nodes. Now coming to the internal nodes, these nodes contain only keys and pointers to the child node. This node only contains key and the block pointers, or you can say the pointers to the child node. It doesn't contains any data pointers, it only contains the key. So it will be K1, K2, K3, K4, and in between there will be some block pointers for this particular children's. Now coming to the leaf nodes, so these node contains keys as well as data pointers. So the leaf node contains keys as well as data pointers, and there is only one block pointer which is present which points to the next leaf node, enabling quick traversal of records. So all the records is present in the leaf node only. If we want to search for any record, we have to just go to the leaf node and traverse the leaf node and find that particular record. What are the advantages of B plus trees? So B plus trees have a balanced structure, meaning all the leaf nodes are at the same level. So all the leaf nodes would be at the same level. This balance ensures that the search operations require logarithmic time relative to the number of keys, making it very efficient even for the large data sets. So even there are large data sets, we store all the data in the leaf nodes, so the traversal is very easy and we can find any data, insertion, deletion, and like reading of the data is performed in the logarithmic time. Now coming to the second point, the structure of B plus trees allows for direct access to the data. Since the internal nodes contain only the keys, searching for a specific value can be done quickly by navigating through the tree down to the leaf node where the data is stored. So in the leaf node, since the data is stored and the internal nodes only have the keys, the leaf node have the key as well as data pointer, and it also has a block pointer which points to the next leaf node. So it helps us to get the data very fast, and the traversal is also very easy. Now B and B plus trees both are used to implement indexes in databases. So B tree and B plus tree both are balanced trees, but there are some differences in the structure of B and B plus trees. So in B tree, all the nodes have the same structure. There is a block pointer which consists the address of the child node, then there is a key, then there is a data pointer which points to the location where data is stored in the hard disk or secondary memory, you can say, and again there are some block pointers. Now coming to B plus tree, so there is some structural differences between the internal and the leaf node. Now in the internal node, there is a block pointer which points to the child address. Then there is a key only which is present. There is no data pointer which is present in the internal node. But when it comes to leaf node, it has a key, it has a data pointer, and again it has a block pointer which points to the next element or next node which is present in the leaf. So basically there is a linked list structure which is formed in the leaf, and in the leaf node only you can find out the data. So let's understand from an example. Think of a B tree as a directory structure on your computer where folders contain both name and pointers to subfolder or files. So consider that there is a directory which is present in your computer. Now there is a folder. So there would be some name for this particular folder. So this is the key of this particular folder. Now in this particular folder, there would be one more folder, or you can say child folder. So we can say that this is the child folder. Now this particular folder is considered to be a node. Now this particular node is containing the key as well as the block pointer, or you can say the pointer to the child which is present here. So this contains the node as well as keys and pointers to the subfolders or the child folders. Now coming to B plus tree. So imagine a library catalog where all book records are listed in a sorted linked list manner, which is leaf nodes, and the internal nodes only contain pointers to guide you to the right part of the catalog. So consider I want some books in the comedy section. So I'll go to this comedy section. Now in this particular comedy section, I can get some books which are sorted in the linked list manner. So this particular comedy section is helping me to find out where all the books would be present, and here I can find the books which would be present in the linked list manner. So I can say that this is the leaf node and this one is acting as an internal node because it is telling me that where exactly these particular things are present. Now coming to the basic differences. So the first one is data storage. So keys and associated pointers to the data are stored in all the nodes. So in B tree, keys and associated pointers are stored in all the nodes, internal as well as leaf node. But coming to B plus trees, all the actual data is stored only in the leaf node. So the data pointer is only stored in the leaf node, and internal nodes only contains keys and pointers to the child node. So internal node we have only keys as well as pointers to the child node. So this is the block point that points to the child node. So we can say that in B tree, all the nodes has the data pointers which is present, but in B plus tree, the data pointers are only present in the leaf node. Now coming to the next point, that is leaf node linking. So there is no inherent link structure which is present between the leaf node. So there is no linked structure which is present between the leaf nodes in the B trees. But coming to B plus trees, leaf node are linked together in a linked list manner. This linked list structure allows for efficient sequential access, making range queries faster and easier. Since all the data is present in the leaf node, we can start our searching from the leaf node, and all the leaf nodes are interconnected with each other, which has key and data pointer. So it would be very easy to search for the data which is present in the leaf node. So searching would be very fast. Now coming to the search performance. So access time can be slower for certain type of queries because you may need to traverse multiple level of trees to find the data. So in B tree, what happens, consider if this is a B tree which is having some internal and some child nodes. Here consider if I want to search for a data, there might be a possibility that I need to traverse the entire data set which is present in this particular tree. But in B plus tree, what happens that since all the data is stored in the leaf node only, we need to only traverse this particular leaf node or the linked list structure which is formed at that particular leaf node. So leaf nodes are linked together in B plus tree, allowing for efficient sequential access and range queries. So it is very helpful for range queries because we need to only traverse the linked list which is present at the end of the tree. Now coming to the space utilization. So since data is stored throughout the tree, B trees might have lower space utilization in the nodes. So since data is stored everywhere, there would be very less space utilization because in a node you need to reserve a space for a key pointer, then the data pointer, and then the block pointer. The storage of key and data pointers in a given node would be very less. Now coming to B plus tree. So B plus tree typically have better space utilization because internal nodes are only used for keys, allowing more keys to be stored per node. So here you have to store key, data pointer, block pointer, but in B plus tree what happens, you have to only store a key and then there are block pointer. So since the data pointer is not stored here, the size of the data pointer which is getting occupied here in the node which won't be needed here. So here we can store more number of keys because there are no data pointers, but here since we have a data pointer associated to a key, there is very less space and very less keys which can be stored in a given node. So these are some of the basic differences between B and B plus tree. Oftenly B plus tree is mostly used in some of the cases because the search performance is very good. We can use it for the range queries. Again, the way in which the data is stored is also very optimal because you only need to go to the last or the leaf node and search for your particular data rather than traversing the entire tree. So this was all about this video. I hope you like this video. So if you like this video, please hit the like button. If you're someone who is new to my channel, can go ahead and watch out the tech content first, and if you find it useful, can go ahead and subscribe. Also, if you have not followed me on my social media handles, you can go ahead and follow. The links are in the description. Till then, take care, keep learning, keep growing, keep smiling. Bye all.